let's get started. So now we have a session with two talks. And the first one will be given by Claire Boyer from Sorbonne University in École Normale Supérieure on various recovery guarantees for compressed sensing.
Okay, can you hear me? Yeah? Okay. So first of all, thank you for the invitation. I'm very pleased to be here. This is a really nice workshop, and I could feel in the participant that the Parisian geography of university was quite difficult. So just let me do a small point. So this is Paris, okay? Here you have the ENS Paris-Ulm. So this is the easy part. Before you got Jussieu, P6, or the University Pierre and Marie Curie, the UPMC, but Pierre and Marie Curie are dead, so is the university, because it has merged with Université Paris-Sorbonne before, and now they are called Sorbonne University. So that's it. Let me skip the talk about the statistical lab and the probability lab. Okay, so I will present a joint work with Adcock and Simone Brugiapaglia, who are in Fraser University in Burnaby, near Vancouver. And yeah, I should say that this is an explicit Beamer team because you may not know, but there are some members of the Beamer fashion police here. And so I've been a very bad girl. I put a background and the title in blue. I'm sorry. Okay, so let's go with the outline. So let me first give my motivation for this work. I will briefly describe the setting, and then I will present oracle estimate and how I deviate from this oracle estimate with my results. Okay, so I will use the MRI as a red thread during this talk. This is my main motivation, but again, you can apply what I will talk about to many different application fields. So just in MRI, we want to reconstruct an image, U, okay? But we only have access to the Fourier domain, to the Fourier coefficient of our image, U hat. And actually, we don't have access to the full Fourier domain. We will just sample along smooth trajectories, parameterized here by lambda. They will have a bounded speed and a bounded acceleration. And so we will subsample here along smooth trajectory. Here it is just a spiral, but you can do straight lines, you can do radial lines, okay, and so on. Okay, so the question is, of course, once you have subsampled your Fourier coefficient, so this is just U hat at the frequency position lambda k delta t. How do you reconstruct U from this set? Okay, so you will notice that I'm far from Gaussian measurements here. Okay, and so will be the talk actually. Okay, so the question is, how do you reconstruct your image? How do you choose the set of sample? How do you handle constraint in the acquisition? Because in practice you have physical constraint on the sensing device. And what is the minimal amount of time or measurements required to get a given accuracy? Okay, of course it has many practical consequences to reduce the acquisition time and so on. Okay, so again, I'm only talking about MRI here, but you could think to apply it to different fields. Okay, if you subsample, and you are willing to reconstruct your image still, you need to have a simple structure in the image that you want to reconstruct. And this simple structure is, of course, the sparsity that you all know. And so in the case of MRI, so this is not an MR image, but let's say, okay, I have this image. I do the wavelet transform of this image. I just keep 1% of the wavelet decomposition of this image, and this is the inverse wavelet decomposition, and I didn't lose much, right? So actually, in practice, real images, brain images, are compressible, are sparse in some good decomposition basis. Okay. So here, for the MRI case, we will suppose that our image U is sparse in the wavelet domain, okay? And we will suppose that W is an orthogonal transform. And so instead of recovering my image U, I will recover the wavelet coefficient of my image because the wavelet coefficients are sparse while my image is not, okay? Okay. So you probably know about compressed sensing. So a way to retrieve your wavelet decomposition is to use an L1 minimization formulation. So here this is a noiseless case, okay? So the basis portrait L1 minimization, or if you have noise, if your observations are corrupted with noise, you can also derive the quadratically constrained basis portrait. And of course, behind the idea of L1 minimization, you want to promote sparsity. And so the question is, what will be the guarantee on the required number of measurements to have exact recovery or robust recovery with high probability. So in this talk, I will only consider L1 minimization, and because I'm more of the school of better choose my measurements instead of fighting in the post-processing computation, okay? So I would talk about structure, but not in the algorithm to reconstruct my image, okay? Okay, so again, just to fix the idea, I want to reconstruct this image, but this is not sparse, so I look at it in the wavelet domain. This is the wavelet decomposition of my image. You see there is a lot of blue means 0, so this is really sparse. But I don't directly observe the image, I observe its Fourier transform and not the full Fourier transform, only partially along radial lines in practice. And in theory, in compressed sensing theory, standard compressed sensing theory, it's IID sampling according to some probability distribution in the Fourier domain, okay? So if I recast the MRI as a compressed sensing problem, I can say that I can model my acquisition, in the case of MRI, with the full sensing matrix A0 to be the Fourier transform times the inverse wavelet transform. And here are just the rows of my full sensing matrix A0, and then I will randomly pick some measurements, meaning that I will randomly pick rows in this full sensing matrix A0, and then I will form my actual sensing matrix A. So my observation is just y equal ax, where x are the wavelet coefficient of the image, and this is the vector that is sparse. Okay. So if I do a brief tour of compressed sensing, the early results were based on uniform drawings, meaning here you just take uniformly at random points, and if you do so in an MRI, you're pretty sure that you will not reconstruct anything. Okay, so this is not really sound for the MRI purpose. Then people introduced a variable density sampling in compressed sensing theory, meaning that you can end with such kind of acquisition scheme in the MRI case, okay? Meaning that you will privilege some frequency here in the low frequency part. You will more sample than in the high frequency part, okay? Meaning that you will sample according to some probability distribution. So here it's P. But later it will be pi, okay? And then we can show that the number of measurements that you need here should be of the order of this, the coherence of your sampling, times S, the degree of sparsity, times logarithmic factor. So this bound is saying that if this is okay, is of the order of 1, then you can sample a number of samples of the order of the degree of sparsity of the true information, meaning that you can really subsample and still have exact recovery or robust recovery. Okay, but the problem is in the Fourier wavelet case, for MRI, here you have a log n, which is not really, which is not so small, and still these results are based on IID sampling, so on isolated measurements that you cannot implement on real devices, okay? So we have to forget about this. And then there is more recent result by Ben Adcock and Anderson, Clarice Poon, and Bogdan Roman, where they they managed actually to kill here a log factor and also to do a variable density sampling here. But this is, so they managed to do so because they restricted the study to a certain class of signal, okay? But still this work is based on isolated measurements, and you can use it in practice on real sensing machines, okay? Yes, sorry.
How are generated these measurements? How are they chosen?
Here, so you just have a probability distribution. It's the same. Yeah. Okay. Yeah, we need probability just to have concentration. Okay, but when you look at paper of compressed sensing, like this one from Lustig, Dono, and Pauli, they are selling compressed sensing because here they subsample and they are doing the L1 reconstruction here. Here is the L2, which is pretty bad. But the L1 is working, but actually there is no current compressed sensing theory explaining why you can subsample like this, such in a structural way, okay, and have still a good reconstruction. Okay, so again, I'm putting the emphasis on, but this is a typical compressed sensing scheme, a theoretical compressed sensing scheme, and okay, it works well. But actually, if I'm structuring the acquisition in the Fourier domain for the MRI case, I can still reconstruct little details that I inserted in my brain, okay? So I'm not doomed. In practice, I'm not doomed by structuring the acquisition. So I should see it in the theory. So I'm not afraid to say that current compressed sensing theories are partially disconnected from application. And she's saying so, I'm not, okay? Okay, so let's start with the setting. So in this talk, we will consider distribution FL, that can be really abstract, and the spaces of PL times n matrices, and we will draw independent matrices B1 to Bm. So I will draw M blocks, M submatrices B1 to Bm, which has a law according to FL, okay? And I will just concatenate these random matrices B1 to Bm. And I need a key assumption here in this work is the block of measurements to be isotropic, meaning that the expectation of B star B should be the identity, okay? So this is the abstract framework, but if I just do it in a case, a very easy case where we are in finite dimension, subsampling and isometry, so let's say that you have A0, the full sensing matrix, okay, which models your acquisition. This is an isometry, but you need to subsample A0 to do as in life, because you have just a subsample set. You can define a block as a rectangular submatrix of A0, and then it means that you will draw a block BK according to some probability distribution pi. So for instance, here, a block may correspond to a straight line, and then I will draw this block with some probability pi, okay? And then I draw another block corresponding to the orange line, and this will be B2, and so on, okay? And in the end, this will be the samples that I take in the Fourier domain for the MRI, and this will be my actual sensing matrix, okay? So of course, this framework is encompassing standard compressed sensing theory, because you can say, okay, a block could be just a row of my matrix, and then I'm just doing like regular compressed sensing theory. I'm taking isolated measurements, okay? So it means that here, you just concatenate blocks that are just rows with some probability distribution, and then you end with standard compressed sensing sampling scheme, okay? So this is just an extension of the standard framework of compressed sensing. So is it sound to extend this setting to block sensing? So in practice I said yes, okay, but actually in theory it may appear at first that this is not a good idea. Why? Consider that you have A0, your full sensing matrix, to be separable. This is the case in the MRI setting. You have the Fourier, which can be seen as a separable transform, and the wavelet could be also seen as a separable transform. And let's suppose that you are taking horizontal line here in n-dimensional space, meaning that you have here square root of n coefficient and square root of n coefficient, okay? You're taking m horizontal line like this. We can show that if m, the number of horizontal line that you take, is less than 2s, the degree of sparsity of your signal, then there is no hope that you can reconstruct your signal. So what does it mean? It means that if I structure the acquisition, and this is from actually the paper of Lustig, Dono, and Poli, so this is the same kind of sampling. If I structure like this my acquisition, I cannot hope to have uniform exact reconstruction for S sparse vector, okay? Because here you see m should be bigger than 2s if I want to have reconstruction, and if 2s is of the order of square root of n, it means that you need to do a full acquisition scheme. Okay, so why do we have this first limitation? It's because most standard compressed sensing theory are only considering sparse signal. They only know the degree of sparsity of the signal, but in practice you don't want to reconstruct any sparse signal, you want to reconstruct very structured signal. So in this talk we do not want to reconstruct any S-sparse vector. So we will derive a compressed sensing theory that can handle structure sparsity, structure acquisition. We will evaluate the number of measurements, of blocks of measurement that we need. We will compare it to the oracle case, and I will try to give insight on how to choose in practice your measurements, theoretically. Okay, for the rest, n is the dimension of my signal x, m is the number of blocks of measurement that I take, and when I write bs, I'm just looking at the column of b that are indexed by s, and when I'm writing vs, this is just a vector where I look at the coefficient indexed by s, where big S is the support of my signal. Okay, let's look at an oracle type result. We can define lambda SF. So S is the support of the signal, F is the way that you draw your blocks of measurements. Okay? Lambda SF could be any bound that is bounding almost surely this quantity, B star B22 norm. Okay? This is just the spectral norm of the B star B. If you have access to an oracle, actually if you know your support S of your vector, you can show that the number of measurements that you will need should be of the order of lambda SF times a logarithmic factor, and then you will have robust reconstruction, robust recovery. Okay? So this is an oracle type result, because if you know the support of your signal that you want to reconstruct, you just have to do a pseudo inverse routine, and that's it. You have your answer, and the stability of the pseudo inverse will be ruled by the lambda SF. So in the sequel, I will say many times maybe oracle type result, but by oracle type I mean oracle type in the number of measurements here, and not in the bound on the noise here. Okay. So there was a previous work from Pierre Weiss and Jérémy Bigot and me, where we consider deterministic sign on the signal. So we define theta SF to be a bound on B star BS infinity to infinity norm. Okay. So this theta could look a bit ugly, but here, okay, I don't know if you see, but here I write theta in the case of block, and actually if you can also write it in the case of isolated measurements, and then it's a mix between the usual coherence, the infinite norm of the rho, times the L1 norm of the rho restricted to the support. Okay, so this is a mix between coherence and support information. And then there is also another quantity called upsilon, and I know that when you look at it, you are saying no, so I won't talk much about this. But let's say that you have a number of measurements bigger than the maximum between theta and upsilon, then you will have a robust recovery in this sense here. So let me comment on this bound later. But first, I just want to comment on the fact that I'm really depending on the support here. So it's really important to depend on the support, because if you remember, I said, okay, if I'm in the separable case, I'm acquiring horizontal lines, and I know that I have a limitation that if I only know the degree of sparsity of my support, then I will need at least a number of measurements to be 2s, right? And then I'm doomed. But let's say that now I have more information on my support, and I know that my support is concentrated on q lines. Then what should be the number of measurements? We can show that the number of measurements with the previous result should be of the order of q times logarithmic factor, meaning that you need a number of blocks of measurements that should be of the order of non-zero lines in your signal and not non-zero coefficient. So let's see a picture here. You have a signal, a sparse signal, which is totally unstructured. Okay, you sample it in the Fourier domain according to our horizontal lines. This is the reconstruction. This is really bad. But now consider another signal with the same degree of sparsity, but now the sparsity is structured along horizontal line. You take the same sampling scheme in the Fourier domain, and you have perfect reconstruction. Okay, so it means that if you structure the sampling, it's okay if you want to reconstruct a structured signal which is adapted to the sampling, but it's not okay if you have non-structured signal. Okay. So don't worry about structure acquisition. This is fine as long as you have the right structure in the support of your signal that you want to reconstruct. Okay, now let me comment about the extra square root of s factor that I had in the noise bound, in the robustness bound. This is a drawback of non-uniform approach. Non-uniform approach are when you are working with the fixed signal and that you don't want to reconstruct any sparse signal. The proof is based on dual certificate using a Gaussian scheme, which is the proof introduced by David Cross for low-rank matrix recovery, and adapted to compressing by Emmanuel Candes and Yaniv Plan. But actually, when you don't do Gaussian measurements, there is no better bound in the literature for this setting. Meaning that if you do non-uniform approach, when you're non-Gaussian, you will always suffer from this square root of s. So we should maybe concentrate on this problem and work on it. Okay, another question is, so I have in the bound of the number of measurements the maximum between theta and upsilon, and this is really difficult to minimize this bound with respect to f, okay? Because in practice, people want to know how to choose the sample, so how to choose f, the probability distribution to draw your blocks, okay? So this is really hard to minimize the maximum between theta and upsilon, so let's try to work on this. So this was the previous result. You have two quantities that are involved. A way to minimize this according to f is just to kill a quantity. So let's kill the ugly one. Let's kill the upsilon. And why? Because it's just the ugliest, and so it's as movie. Let's kill it. Okay. So first, I should mention that this is an ongoing work. So please be indulgent. But you can be critical, meaning that you just say mean things, but you have to put it in a nice way. And and finally, don't steal the result because it's me. Okay. So you remember theta. Theta is just a bound on B star Bs in the infinity to infinity norm. Then I can show that if the vector that I want to reconstruct is supported on S, and such that the sign on the support forms a Rademacher or Steinhaus sequence, then the number of measurements, of blocks of measurement required should be of the order of theta SF times logarithmic factor, and then I will have robust recovery for non-uniform approach. So how much are we off the oracle? Of course, we have the square root of S here, but still I won't comment on this. I don't know how to do better for now. We have also a log factor here of the oracle, and we have theta instead of having lambda, where lambda is bounding the spectral norm and not the infinity to infinity norm. Okay. So let's, once you have this, you can say, okay, I want to minimize theta with respect to f, okay, to minimize the number of measurements that you need. And then you will have your optimal way of sampling your signal. Okay? So if you do so, you can, in the case of an isometry, if you're subsampled on isometry, in the case of block, it means that you should choose the kth block with the probability pi k star, which is proportional to the infinity norm to infinity norm of b star bs. Okay? And in the case of isolated measurements, I just rewrite the thing for standard compressed sensing. You should choose the kth row, the kth measurements with probability a infinity norm times AS L1 norm. Okay. If you do so, you end with a minimal amount here on the number of measurements, or of block of measurements here, of isolated measurements here. Okay. So let me do a brief history of optimal sampling for standard compressed sensing, and still Fourier and wavelet can be tricky to have in mind. So I will focus on a sampling matrix, which is just the first vector of the canonical basis here, and then the Fourier transform in n-1 in dimension n-1. Okay, so it means that here I have something which is really coherent, because here you will localize very much the information, and here I have something which is really nice, a Fourier transform, so that will spread out the acquisition, the information, sorry, meaning that if I have something really sparse here, then it will be spread out in the output with this transform. Okay. So in the seminar paper, they do uniform drawing. If you do uniform drawing with such a matrix, meaning that you choose row AI with probability 1 over n, you will end with the number of measurements to be of the order of s times n, the dimension of the signal, times logarithmic factor. You're doomed. You cannot use it. Okay, now later they introduce variable density sampling due to variable coherence, meaning that you choose you should choose your sample according to the maximal L infinite norm of the row. So for the first row, you should choose it with probability 1/2, and for the other one, you should choose it with probability 1/2, 1 over 2 times n-1. And if you do so, then the number of measurements will be of the order of 2s times logarithmic factor, and then it's cool. Okay. So here, we sample where the sensing matrix tends to localize the information, saying that with probability 1/2, you would take, in an IID sampling, the first row, okay, the first vector of the canonical basis. But now with the new result, we have to sample according to the infinity norm times the L1 norm of the vector restricted to the support, and then you will end with such a bound. But it means that if you have no information on the support localized on the first coordinate, then you can you can reduce the probability to choose the first row. Okay, so this result is saying, okay, you should sample more if the sensing matrix tends to localize the information. This is this term, but if there is information here, which is this term. Okay. Okay, so this is really the take-home message. The optimal drawing probability should depend on the local coherence of the sampling transform, okay, and the sparsity structure of the signal. And this is the same for the block case, but it's just easier to illustrate it in the isolated measurement case.
So S is a fixed pattern?
Is a fixed support. It's a fixed support, but you can say that it belongs to a class.
But then you maximize about the class?
Yes. Yes, I'll do an illustration on the MRI case. So what happens for Fourier wavelet transform? So we can say that A0, our full sensing matrix, is Fourier, the Fourier transform times the inverse R transform. Sorry, yeah. We can define subbands or level from the wavelet decomposition called omega L, and we can define sparsity by level or sparsity by subband to be SL. Meaning that the support restricted to the L level has a degree of sparsity less than little SL. Okay? And actually, in this case, in the case of Fourier and R, I can do an estimation for theta, which is here. And once I have my estimation for theta, then I can say, okay, my optimal probability drawing is here. So when I'm in the case position in the Fourier, the case frequency should be sampled proportional to what? Proportional to the degree of sparsity of the corresponding subband of the wavelet decomposition, plus some perturbation term where you have the other sparsity in the other subband that are interfering, but they are their action are minimized by this quantity. And if you shoot this way of drawing your measurements, then you will need a number of measurements of the order of the sum of the degree of sparsity plus an error term. Okay? So really the number of measurements here for a given frequency should be proportional to the corresponding degree of sparsity in the corresponding wavelet scale plus some interference terms involving sparsity in other scales. Okay? So let me do an illustration here. Suppose that we have three subbands in our wavelet decomposition, and we have this kind of pattern for the support, meaning that in the first level we have a high sparsity, and when we go to level 2 we have less and less sparsity. Okay. So I will generate like 100. No, sorry. No, here this is not it. Okay, so I'm just supposing that I'm interested in signals that are structured like this, that have a structure sparsity like this. This is the typical probability distribution that you should use in Fourier domain. So here you have the low frequency and here you have the high frequency, according to the former coherence probability distribution. Okay. So meaning that you're just looking at the infinity norm of the Fourier times wavelet transform. Now, if you suppose that you have information of your signal, which are structured like this, okay, this probability distribution becomes like this, okay. So it really changed the way of you will sample your frequencies. Okay, so I try to discuss a bit about the oracle type result. So you recall that lambda SF could be defined as the bound on the 2-2 norm of B star S BS, and you can also define another quantity. And if you can show that lambda satisfies this inequality, then the number of measurements that you need to have reconstruction should be of the order of lambda SF times logarithmic factor. So now we have an oracle type result in the sense that here we have lambda, the 2-2 norm of B star S BS, okay, but we still have a log factor, an additional log factor. How to kill it? Well, you can just modify the condition here by introducing a log factor, and if you satisfy this condition, you will have an oracle type result. But now the question is, can we really satisfy this kind of condition, right? So in the case of Fourier wavelet, again, for the MRI, you can show that you have both conditions as soon as the degree of sparsity by subband is bigger than a logarithmic factor. So it means that instead of optimizing your probability distribution according to theta, you will optimize it according to lambda. And what is the gain to optimize with lambda, the 2-2 norm, instead of the infinity to infinity norm? You will kill more the perturbation terms here, okay? And then in the number of measurements, you will need less measurements by killing here the perturbation term a bit more. Okay, so again, let's just see what happens in a numerical experiment. I take the same structure support pattern here, okay? So I'm structured by wavelet level. This is the standard way of drawing your frequencies in a random way. This is the way of drawing your frequencies according to theta, and this is the way to draw your frequencies according to the oracle type result depending on lambda, okay? And if I compare the reconstruction according to the three different ways of drawing my samples, here you have the usual way, here you have the theta way, and here you have the oracle type lambda way, okay? So of course we improve the reconstruction. Okay, so I will do some concluding remarks here. If the assumptions that I show to you to have oracle type results are not verified, I still have some trick in my bag and to get oracle type result, but I won't discuss about this today. We can also extend the setting to the setting where you will sample partially deterministically. This could be of interest in the case of Fourier wavelet again, because you want to saturate the low frequency, and then you will take at random when your random samples when you go towards high frequency. Okay, so what I said can be really extended to this setting, which is of practical interest. And actually, by doing so, you avoid the coupon collector effect since you saturate partially your sampling. Okay, I did not talk about stability, and of course it would be nice to remove the random sign assumption to get still oracle type results, but that's the only way that we found to have oracle type results. And of course, a big question that I'm interested in to make a robust and stable non-uniform approach when you're not considering non-Gaussian measurements. And the only work that I know that are really robust and really stable are for Gaussian measurements, but they involved the statistical dimension, and this is really hard to evaluate these kind of quantities when you structure the acquisition and you don't have Gaussian measurements. Okay, I'm ready for your questions, but please, you must ask the right questions. Thank you.
We have time for the right questions.
No right question.
Can I ask a mean question?
A mean question?
Mean question.
Oh, okay.
Politely, yeah. This is very
Thank you.
So you started by saying that you want to make contact with practice where you can achieve 30 reconstruction of your image with 13%. If you use your theory, you get in your bound, you get 13% of measurements.
Oh, you mean by evaluating the constant? Not exactly. I mean, you can have it for a certain resolution. So actually, when we think about standard compressing sensing theory and also this, since we have concentration tools behind, these are results that are interesting. Sorry, only when you have high resolution, so really high N, really high dimension. Okay, but this is true when you have low resolution. All compressing sensing theory results are irrelevant actually, because the logarithmic factor and the constant in front are too big for the bound.
It seemed like some of the sampling schemes, as Francis asked, depended on the set S, the true support,
Yes.
right, to be optimal. Is there a way you could do, so certainly you don't know that ahead of time. Could you imagine like a two-phase procedure where in the first phase you kind of vaguely estimate what it is, and the second phase you dial down? Is that a...
We're trying to do so actually so we're trying to do so not for compressing sensing but for function interpolation. But it's not so convincing, so that's why I didn't talk about this. But yes, we have this in mind, of course. Yeah.
I have a question. So have you considered using a different norm than the L1 norm? Because if you know a bit about the support, you can define a norm which is dedicated to that type of support.
No, I didn't try. It was really a way that, okay, I don't want to adapt my reconstruction procedure. I just want to adapt my measurements. But of course, if you have some structure on the signal, you could try to enhance it in the reconstruction algorithm.
Since you have different frequency subbands, you could imagine having a different weight on the L1 norm for all of the subbands.
Yes.
And it could improve quite a bit.
But I prefer to do so because when you write the theorems in the general setting, it means that you can apply it to very different application fields. So I only talked about MRI, but you can do it for for much more application fields, and then you can just try to compute the bound, because I don't know which are the right structure support for a particular application. So.
Any other questions for Claire? Thank you again.